Interstellar exploration has long been a powerful dream that ignites the imagination of humankind. The idea of reaching another star system, such as Alpha Centauri, has fascinated scientists, visionaries, and storytellers for decades. But the vastness of space poses monumental challenges. How do we overcome the nearly unimaginable distances between stars? What kind of propulsion could possibly carry us beyond our solar system? This is where a groundbreaking new concept known as the Sunbeam mission enters the conversation. It introduces a revolutionary approach, using relativistic electron beam propulsion to send spacecraft beyond the boundaries of interstellar space. In this video, we'll uncover why the Sunbeam mission is not just another theoretical idea, but a bold leap forward for humanity's journey to the stars. We'll explore the science behind it, the mechanics of its propulsion system, and the real-world innovations that could make this vision a reality. What sets Sunbeam apart is its ambition, not just to launch a probe, but to redefine how we move through the cosmos. At the core of the Sunbeam concept lies a cutting-edge propulsion method, the relativistic electron beam. This system relies on streams of electrons accelerated to speeds approaching that of light. When directed at a spacecraft, this powerful beam delivers sustained thrust, allowing the vehicle to reach incredible velocities, up to 10% of the speed of light. To put that in perspective, this could enable a probe to reach Alpha Centauri, our nearest neighboring star system, within a little over 40 years. That's astonishing when compared to the thousands of years it would take with conventional propulsion. But why use electron beams at all? Unlike traditional rockets that must carry heavy fuel, the Sunbeam mission externalizes its energy source. This dramatically reduces the spacecraft's mass, enabling much faster acceleration and extended endurance. Moreover, electrons are comparatively easy to accelerate, making them an efficient choice for relativistic propulsion. This approach transforms how we think about deep space travel, where the energy source doesn't travel with the ship, but follows it from afar. The physics behind this concept is equally remarkable. At such extreme speeds, a phenomenon called the relativistic pinch effect comes into play. Ordinarily, electrons repel one another because of their like charges. But at near light speeds, time dilation alters their interactions. This slows down the repulsive forces, allowing the beam to remain tightly focused and coherent across immense distances. That coherence is vital. It ensures the beam continues to push the spacecraft steadily, even when it's far from its source near the Sun. This makes Sunbeam fundamentally different from projects like Breakthrough Starshot, which use laser beams to propel extremely lightweight probes equipped with light sails. While innovative, those probes, typically just a few grams, lack the capacity for meaningful scientific instruments. By contrast, Sunbeam envisions propelling a spacecraft weighing up to 1,000 kilograms, roughly the size of NASA's Voyager probes. This opens the door to a new era of scientific exploration, where fully equipped spacecraft could conduct in-depth investigations of other star systems. A pivotal component of the Sunbeam system is the statite, or stationary satellite, positioned close to the Sun. Unlike satellites that orbit, the statite remains fixed in place by balancing solar radiation pressure and magnetic forces. From this unique location, it can precisely aim and direct the relativistic electron beam at the spacecraft. To survive the Sun's intense environment, the statite is protected by a massive heat shield that safeguards its delicate systems. This sophisticated platform plays a critical role in maintaining the beam's accuracy and direction over long periods, essential for keeping the spacecraft on course. Of course, turning this compelling vision into reality isn't without challenges. One of the most significant is generating and maintaining a high-energy electron beam across interstellar distances. The beam might require energy levels of up to 19 giga-electron-volts at distances as far as 100 astronomical units from the Sun. While these levels are technically achievable with current particle accelerator technology, such as what we see at the Large Hadron Collider, maintaining a coherent beam over such massive distances is entirely new territory. To power the beam, the statite must harness the sun's energy with exceptional efficiency. This would involve converting intense solar radiation into usable electrical energy through advanced systems like high-temperature thermionic converters. These converters, designed to function near the sun's extreme heat, are currently under active development. Their success will be vital to making the Sunbeam mission viable. The spacecraft itself must also be fundamentally reimagined. Unlike conventional designs that rely on internal thrusters, the Sunbeam probe must endure continuous external thrust from the electron beam. This demands advanced navigation and stabilization systems to keep the probe aligned and ensure accurate trajectory adjustments. The materials used in its construction must also withstand extreme conditions, especially for the statite. Radiation levels and temperatures near the sun can soar above 2,500 degrees Fahrenheit. Missions like NASA's Parker Solar Probe have already demonstrated that durable heat-resistant materials can survive such environments. These breakthroughs will serve as the foundation for engineering components of the statite and spacecraft. Another challenge is beam divergence. Over interstellar distances, even a slight spreading of the beam could result in a loss of propulsion efficiency. Solving this issue will require precision engineering and an in-depth understanding of beam dynamics to keep the stream of electrons narrow, focused, and effective throughout the spacecraft's journey. Despite these hurdles, the Sunbeam mission remains within the grasp of current or emerging technology. Its success will depend on collaboration across disciplines, bringing together experts in particle physics, materials science, aerospace engineering, and solar energy systems. This is not just a theoretical experiment. It builds on decades of innovation and hard-earned scientific progress. Consider the Parker Solar Probe, launched in 2018. It ventured closer to the sun than any previous mission, enduring conditions once thought impossible. Its success has given scientists invaluable insights into solar radiation and energy collection near the sun, insights that directly support the development of the Sunbeam statite. In the realm of particle physics, experiments conducted at facilities like CERN have pushed the boundaries of what's possible with all high-energy beams. These research efforts have deepened our understanding of particle acceleration, beam coherence, and energy transmission, all of which are critical for the Sunbeam propulsion concept. The Sunbeam mission also connects with other beam-based propulsion projects, such as the Deep-In, Directed Energy Propulsion for Interstellar Exploration program. Though Deep-In focuses on laser beams rather than electron streams, its research into energy delivery, alignment, and long-distance beam control shares many parallels with Sunbeam. Together, these efforts demonstrate how diverse scientific fields are converging to make interstellar travel no longer a fantasy, but a fast-approaching reality. By capitalizing on these recent breakthroughs, the Sunbeam mission reveals a bold pathway forward, not only for traveling to distant stars, but for revolutionizing how we understand physics, develop materials, and harness cosmic energy systems. The potential impact reaches far beyond space exploration. It represents a defining step for humanity's future among the stars. Thank you for joining us on this journey through the frontier of science and imagination. If this mission excites you as much as it does us, don't forget to like, share, and subscribe to Space Future Now. Together, let's keep pushing the edge of what's possible and beyond.